Hey, thank you everyone. I'm Steve, and today I'm here to talk to you about some breakthrough technology we've been, working for LLMs, which, hopefully in our hopes, pave the way for unlimited context. First of all, we are ZML or ZML, depending on which side of the Atlantic you're watching. We are building this universal inference stack and engine. So essentially, it's like literally the same code, the same binaries even, that runs on for any models on any language. Any chip. Any language model or any model on any chip. But this is not what I'm here to talk to you about today. Today we're going to do a little bit, of a deep dive into Llama and also probably one of what we think is one of the most fundamental problems in LLMs today. So this is the Llama architecture. So usually every time you generate a token, this happens. That loop you see in the middle is for each layer that happens. What we're interested today is one mechanism that is fundamental to the way Transformer works, and it's called attention. This thing happened at every single layer. There's a few operations on each layer, but this one happens every layer, and it has a tiny problem. This is the mathematical formula of attention. You don't need to get into the details, but the problem we all have with attention, and ultimately that binds everything we see from the hardware to the reason there's a context window, etc., is because that algorithm runs in quadratic complexity. Which means for everything you add to the algorithm, you get to do the square of it. And that makes us pretty sad and also pretty limited in what we can do. But there's something, about that formula. Like if you squint your eyes real quick, you might see something that is of interest. And that interest is the softmax, right? So what's with the softmax? Well, this is the equation of the softmax. And long story short, you don't need to read it, but it's essentially exponential of all the elements divided by the sum of the exponential. And what that means, it means that tiny signals becomes a lot bigger. And what is the end result in the end? The end result is that this is an actual, output of an attention for tokens. And what you can see is that it's mostly sparse. There's a lot of empty room. So there's, in the end, a lot of completely close to useless calculations that are being done every time you run that algorithm. So, as an ex-engineer, ex-backend engineer myself, I look at this and I squint my eyes and I see, well, is this a graph really? Could we only do the yellow dots, right, and not do the black dots, right? The GPU will compute everything. So, is this a graph, right? And turns out, yes, it is. Very much a graph. It's a graph in latent space, but still a graph. And what's very cool about the fact that, if we model this thing to be a graph problem instead of a pure raw matrix multiplication, is that we can run it in log of n. And as you can see on that graph, log of n is, flattens as the context sizes augments, right? And this, paves the way for unlimited context, ultimately, because it's log of n and it's not, n square anymore. But it's very nice, very promising, but there's this tiny, tiny problem. The tiny problem is that because it's a graph, we need branching. And this means that for this, GPUs are close to useless. They're very bad at branching. They can do it, but if you have worked on GPUs, you might understand a bit deeper why. But CPUs are good, right? And we get into this thing in which we might do the calculation and we might model this as a graph problem, but only on CPU. So the question is, can we do it fast enough? Now, maybe. Let's do some math real quick. So this is the per layer. This is a layer of Llama. And what we see is there's 32 of them in an 8B. If we want to run it at 100 tokens per second, that is 300 microseconds per layer. Now, this is like our time budget if we want to achieve that throughput, which is roughly 5090 territory. If we look at everything around attention, we see that already 200 milliseconds is off the equation because of all the other operations. That leaves us about 100 microseconds to do the actual, calculations and the actual attentions. That's not a lot of time, right? So the question becomes, is it enough? Like, do we have enough time to do the calculation of attention? Number one, like the vector and the matrix multiplication, etc., as a graph on the CPU, and all of this in less than 100 microseconds. And actually, we can. And the reason we can is that because we only compute essentially the yellow dots, right? So this is what you see as a trace of a whole one layer. And so that is pretty interesting, or at least encouraging, because we only spent about 30 microseconds doing the actual calculation. And remember, we skip the black parts. But there's another side benefit to that, because if we run the attention on the CPU and not on the GPU, it means that we have more GPU memory. In this case, if you run a model on the GPU, you have part of the GPU dedicated to the model, and part of the GPU, sometimes the majority of the GPU, dedicated to the KV cache. That creates a plethora of problems for those who are deploying LLMs in production environment, static routing, and all of these things. But if we do the attention on the CPU in system memory, then suddenly the KV cache doesn't need to live in the GPU, which gives us more memory for the model, and actually makes also the model completely stateless. The GPU, sorry, completely stateless. And so in this case, KV cache now lives as system memory. The GPU will send data to the CPU. The CPU will run the calculations, update the KV cache, and send back the attention to the GPU. But there's another catch to this, is that we are in need of a lot of CPU cores then, roughly about 1 per KV head. So the question is, like, how do we get these cores? Like, let's say we want to do a batch run. So perhaps, is there a way we could get these cores, maybe not locally on the machine, which has sometimes, underpowered CPU because they're pretty much useless, except for PCI lanes, maybe. But could we get them, like, these cores somewhere else? Because remember, now the attention and the KV cache is completely separate from the GPU. And so maybe, could we get, the CPU power over the network? Remember, we spent about 30 microseconds or so on the raw calculation. That leaves us about 70 microseconds to, let's say, to attain this throughput. So let's do, is physics on our side? Not easy. Let's do some calculations. So roughly, the payload we would need to send is the number of, attention heads, KV heads, etc., which is about 10K for an 8B per layer, per request. Now, let's be conservative about this, and maybe we're running on a 10 gigabit internet connection, right? So no InfiniBand, no crazy stuff, somewhat, I would say, premium 10 gigabit, but it's not the end of the world, and it's not very, I would say, unattainable. And physics tell us that we could run this thing, at least do the round trip of the data, would go at about 16 microseconds. So suddenly, we might ask ourselves, are we ready to spend 15% of the time budget on essentially unlimited CPU cores because we can provision and unprovision them over the network? I think that's a pretty good deal, if you ask me. And so this is what it would look like. So you would do the calculations, the dense calculations on the GPU, then extract the data, send it over the network as UDP, of course, because you want to be compatible, feed it to the other machine, compute the attention on the CPU, and send everything back. And you need to do this faster than the GPU would calculate it himself. Now, the reason we cheat is that we do much less calculations than the GPU would. So, let's try it, right? Let's do a ping. And, oh crap. So, physics is on our side, but engineering obviously isn't. So how do we square that circle, right? something's got to give. There must be something we can do because, physics is on our side. We're not, at least at this point, we're not fighting physics. So maybe we have a little trick up our sleeve we can pull. And it's time for kernel bypass. And so the Linux kernel, we are at this stage, thankfully for us, or maybe not so thankfully for us, at which the Linux kernel might be too slow for what we are trying to do. There's too much latency. And so this is where we enter another technology in the mix, and it's called DPDK for those who recognize it. What it allows for us is directly talk to the network card in a way that is very, very low latency. The driver is actually built inside the application itself. And what this allows us is to get much, much closer to the theoretical latency. So theoretical latency in this case would be about 16 microseconds. We get about 20 measured. So that is, still within the budget. And this is exactly what we've been building. And we call it attnd. And the clicker has a slight lag. And if you're up for it, I'm here to give you a demo. Are we good? All right. So just so you know, this is what it's running on. Right? So what you see is like a machine with GPUs and a machine without. All the attention is running on the machine without the GPU. So nothing is missing, right? So let's crack this one. Can you see it? Nope, but it's fine because I can do this and that. Right, okay. All right, so of course this is a video because demo gods, right? But what you see on the left is attnd running. On the left machine, you see all the cores 100%. And what you'll see on the right is a standard llama model running standard inference. There's nothing happening on the model side. They're communicating over the network, and I'll let you see what it, how it performs. So we're loading the weights, and then off it goes. But where's my? I have lost the quick time. Okay. But we're not done. I think you are in luck because maybe we can do a little bit more than this. You see, the KV cache is not on the GPU anymore. That leaves us more room. So maybe what if we could fill the entire GPU without any, room for conversation and room for the KV cache, only the model, completely stateless on the GPU. And so this is what we have for you, a live demo. I'm actually going to do, as we speak, in which we're going to run a 32B model, FP8, on a 32 gigabyte GPU, which is, as far as we know, has never been done. Because it's useless in the real world, except if you have this. All right, so, I have the feedback here, good. So are we live? Okay. Hopefully the Wi-Fi is with us. So I'm gonna run attnd on the bottom terminal. Yeah, it's live. And on the top terminal, I'm going to run a 32B model, Qwen 3 32B, on a 32 GPU. Just so you know, 32 gigabyte GPU. Just so you know, that model fits, when it's done loading, there's 20 megabytes remaining in the GPU. So essentially useless. So let's try it. I'm going to tell it to write an MLP CUDA kernel. Hopefully it doesn't crash. It crashed. That's how you know it's a real demo, right? And there we go. So just so you know, this is, as far as we know, it's the first time it's ever been done. That model isn't supposed to run. Thank you. So, and just so you know that it's not, a fake thing, I'm going to kill attnd, and yes, generation stops, because it's now, shooting packets into the void. All right, let me just go back. So the demo gods were with us today. Pretty good. Thank you very much. That is us. Feel free to, or be sure to check out our repo. This is open source technology. And, would love to see you part of the community. Thank you.